Hello, I'm Professor Nagnath Hulle, and in this particular video we will discuss about the design of the serial adder using Moore model. In the previous video we discussed about the Mealy circuit design. First I will just discuss about the Mealy model and then we will come to the design of the Moore model. In the previous video we have already discussed about the Mealy model, and in this case, look at. This is the stable state A and this is the stable state B. And in case of the Mealy model, the output changes in between the states. For example, we are in the stable state A. Whenever inputs are 1, 1, its output will become 0 and then the circuit will reach to the stable state, that is B. Means output changes in between the states. That's why the number of states are nothing but things which we have to memorize. As in case of the serial adder, we have to memorize the carry, and carry has the two possibilities, that is carry is equal to 0 and carry is equal to 1. That's why we have only the two states. But in case of the Moore circuit design, what we have? In case of the Moore design, the output is stable. Output is stable for each state. Therefore, the possible number of the states will be equal to the things which we have to memorize plus the possible number of the outputs. I will come to this slide. Now look at here. Now here in this case, we have two things which we have to memorize, that is carry is equal to 0 we have to memorize, and we have to memorize carry is equal to 1. At the same time, for carry is equal to 0 we have the two possible combinations of the outputs, that is output is equal to 0 and output is equal to 1. Similarly, for carry is equal to 1, again we have the two possible combinations of the outputs, that is carry is equal to 0 and carry is equal to 1. That's why the number of states are more in case of the Moore design as compared to the Mealy design, because in case of the Moore design, outputs are fixed to the stable states. That's why the number of states is equal to the number of things which we have to memorize plus number of possible outputs for that particular things which we have to memorize. This we have to memorize carry is equal to 0, we have the two possible combinations of the outputs, carry is equal to 1 we have to memorize, and we have the two possible combinations of the outputs. That's why the total number of the available states in case of the Moore design for the serial adder will be the 4. I will come to this slide, I will go back. Now look at what we have considered. I have considered present state, and this is the next state, and then we will check what happens. Now here output present, what is the each state indicates? Each state indicates itself is the thing which we have to memorize plus output is nothing but the state. We have 4 possible combinations. Here we have 0 0, then we have 0 1 combinations, then we have 1 0 combinations, and we have 1 1 combinations, means we have possible 4 states. Then we have the inputs are 0 0 0 1 1 0 1 0 1 1 for 0 state, then 1 state, then 2 state, and then 3 state. Now we will check the possible combinations of the next state. Now here that I will discuss in the same slide, and here this table is nothing but the truth table for the full adder. Now here I will start with the first. We are in state A. What is the state A? State A is nothing but carry 0, output 0. Look at state A. Carry 0 and output 0 is the state A. In the state A, whenever inputs are 0 0, this is present state. When the inputs are 0 0, now look at how we are calculating the output. we are calculating the output x0 plus y0 plus previous carry, which is 0. Now look at previous carry x0 y0. What will be the sum and what will be the carry? Sum will be the 0 and here its carry will be the 0. That's what we have. Sum is 0, carry is 0. Means what is the next state? Next state is again 0 0. Means when we are in the A state, then for the 0 0 input, the next state will be the same state, that is A state. Similarly, whenever we are in the A state, input is 0 1. What is the carry? Carry is the 0, previous carry. Then inputs are x and y, that is 0 and 1. 0 and 1 means here in this particular case, sum will be the 1 and carry will be the 0. Here sum will be the 1 and carry will be the 0. Means what will be the next state here? The next state will be 1 0. Sum is 1, carry is 0. Here this is sum is 1 and carry is 0. Sum is 1, this is sum is 1 and the carry is 0 is the next state. Now look at which is the C state. Means whenever we have 0 1 as an input, look at here 0 1 as an input, in that particular case the next state will be 1 0. That is nothing but output is equal to 1, that is sum is equal to 1 and carry is equal to 0. Similarly, whenever we are in the A state, input is 1 0. Input is 1 0. What is the carry? Carry is 0. This is 1 and this is 0. If we are adding, sum is 1 and carry is 0. Sum is 1 and carry is 0. That is 0 1. Sum is 1 and carry is 0. Means here it is 1 0. 1 0 is nothing but C state. This next state will be again the C state. For 1 0 also, let's look at here. For 1 0 also, the next state is the C. Similarly, for 0 1. Present state is the A. Why it is A? Because sum is 0, carry is also 0. Here, sum is 0 and carry is 0 is the state A. Inputs are 1 1. Now here, this carry is 0. Carry is 0. X is 1, Y is 1. How much is the addition? Sum is the 0 and here its carry is 1. Sum is the 0 and carry is the 1. Means what is the state? State is 0 1. And if the state is 0 1, 0 1 means output is 0 and carry is 1, that is a B state. Means whenever we are in the A state, inputs are 1 1. In that particular, next state will be the B state. In that case, next state will be the B state, which we have shown here itself. This is 1 1. The next state will be the B. Then if we are moving further, in this particular case, now look at here. Present state is 0 1. What is 0 1? Present state is 0 1 means present state is 0 1 means in this particular case output is 0. Now look at output is 0 and carry is 1 means B state. Means 0 1 is the B state. Means whenever we are in the B state, inputs are 0 0. Inputs are 0 0. How is the addition? What is the carry? Carry is the 1. Inputs are 0 and 0. Means here its addition will be the 1 and its carry will be the 0. Sum 1 and carry will be 0. Sum 1 and carry will be 0. Sum 1 and carry 1 will be 0. This is nothing but 1 0. And 1 0, this is 1 and 0 is nothing but state C. This for 0 0 input, the next state will be the C state. Further, whenever we are in the B state, inputs are 0 1. Now look at 1 0 1. This here 1 0 1 its summation. 1 0 1 its summation is sum is the 0 and its carry is the 1. Sum is 0. This is sum is 0. Carry is the 1. That is 0 1. Sum is the 0. Sum is the 0 and carry is the 1. Means we are in the B state. This for 0 1 input we will remain in the B state and so on. Now here in this case, For 1 0 input for the same state, for 0 1 state, that is when we are in the B state, input is 0 1, then again 0 1 will be the state, that is nothing but B will be the state. Then for 0 1 state, when the inputs are 1 1, the next state will be 1 1. Now look at here how this 1 1 carry is 0, this carry is 0, this x is 1, y is 1, this carry is 1, carry is 1, here carry is 1, this carry is the 1, x is the 1, y is the 1, 1 plus 1 plus 1 is the 3, that is sum is 1, and carry is the 1, that is 1 1, and here sum is the 1 and carry is the 1, that is D state. Means whenever we are in B state, inputs are 1 1, the next state will be 1 1, which is nothing but the D state. Next state will be the D state, and so on. Means in this way, for each possible state, we are able to calculate its next state, and we are able to complete the state diagram. I will come across this, and finally, whenever we are in 1 1, that is nothing but state D. Whenever we are in the state D, in this state, inputs are 1 1, state D, inputs are 1 1. We are interested in carry only. In state D, what is the carry status? In state D, the carry is 1. What is x and what is y? X is 1, and y is also 1. How much is the sum? Sum is 1. How much is the carry? Carry is also 1. The sum is 1 and carry is 1, means 1 1, and 1 1 is nothing but sum is 1. Look at this, sum is 1 and carry is 1, means we will remain in the D state itself. That is nothing but, for final case, we will remain in the D state itself. This is the preparation of the state diagram. Means in case of the sequential circuit design, it is very important to find out the possible number of the states. In case of the Mealy model, the possible number of the states will be the things which we have to memorize. And in case of the Murray model, the possible number of the states is equal to, or possible number of the states are equal to, the things which we have to memorize plus which we are memorizing has a different combinations of the outputs again. Means we have to use that both combinations together, and that will give the possible number of the states. In design for the serial adder, the number of states is equal to the 4. And this is the preparation of the state diagram. Now here, if we have the state diagram with us, we will prepare, that is the output, because in case of the Murray model, the output purely depends on the present state of the machine. Now look at, whenever the present state is 0, means A, what is the output? 0. That's why its output will be 0. Whenever the present state is 1, that is B, its output will be again 0. Whenever present state is C, look at here C, its output will be 1, that is output will be 1. And whenever the present state is D, its output is again 1. Look at here, its output is 1. In case of the Murray model, this sum or whatever, this output only depends on the present state of the machine. If the present state is A, output will be 0. If the present state is a B, output will be 0. If the present state is a C, output will be 1. If the present state is a D, output will be 1. And this is useful in the further design. Now, after preparation of the state diagram, we can prepare the state table. Just that is for state A, 0 0 input, next state and output. For state A, always output will be 0. For state B, again output will be 0. That is straightforward. For state C, look at here, output will be 1. This. And for state D, again output will be 1. We will discuss about remaining things. Now whenever we are in state A for 0, 0 input, next state will be A. For 0, 0 input, next state will be A. For 0, 1 input, the next state will be C. For 0, 1, next state will be C. For 1, 0 also, the next state will be C. Look at here, for 1, 0. And for 1, 1, the next state will be B. For 1, 1, the next state will be B. Similarly, whenever we are in the B states, for 0, 0 input, the next state will be C. Look at here. For 0, 0 input, the next state will be C. For 0, 1 input, next state will be B. For 0, 1 input, the next state will be B. For 1, 0 input, the next state will be again B. For 1, 0 also, the next state will be B. For 1, 1 again, the next state will be D. For 1, 1 again, next state will be D. Whenever we are in C state, for 0, 0, next state is A. For 0, 0, next state is A. For 0, 1, next state is C. This is. For 1, 0 again, next state will be C. For 1, 0, next state will be C. For 1, 1, next state will be D. For 1, 1, the next state will be D. And finally, for D state, for 0, 0 input, the next state will be C. For 0, 0, next state will be C. For 0, 1, it will be B. For 1, 0 again, it will be B. This is 1, 0, it will be B. And finally, for 1, 1, it will be in the D state itself. By this way, we are able to prepare the state table from the state diagram. After the preparation of the state table, we can prepare the state assignment table. Now look at how many states we have here. Here we have 4 states. State A, State B, State C, and State D. We can give any number or binary number to each state. We have the 4 states that we need the 2 digit at least. That's why here I am naming the A state as 0, 0, B state as 0, 1, C state as 1, 0, and D state as 1, 1. Just we are giving the binary number. Then here A state will become 0, 0. Here this C will become 1, 0, C 1, 0, B 0, 1, and so on. We will give the number. Remaining everything will remains the same. Means we are giving the binary number. Again here we are also able to calculate the possible number of the flip-flops required. The possible number of the flip-flops required is nothing but here we need the 4 states. We need the 4 state. That is equal to 2 raised to power of small n. And this n will be the 2. This here in this case we need the 2 flip-flops for this particular design. Now compare the number of flip-flops required in this Murray design and in case of the Millet design. In case of the Millet design, number of the required flip-flops will be the 1. And here in this particular case, the number of flip-flops required will be the 2. That's why in case of the Murray design, the hardware requirement is the more. After preparation of the state assignment table, we will prepare the design table. Now look at here. This is the state assignment table we have copied as it is. And just what I have done here, this PS, that is present state, has 2 digits that I have separated. That is PS1 and PS0. This is X and Y are the inputs which are same. This is X and Y. Then we have again NS, that is next state, we have the 2 digits. That is, I have made it as NS1 and NS0. And this sum, which is as it is. Here, whatever the values we have here, 0, 0, we have the same thing we have copied here. And finally, for 1, 1, the same values we have taken here. Remaining things are same. Now, what do you mean by the design table? In the design table, we are trying to find out the excitation for a selected flip-flop. Now here, in this case, we have the 2 next states. That is NS1 and NS0. Means here, in this particular case, we need the 2 flip-flops. And for this 2 flip-flop, first flip-flop I have named it as T0. That is a T flip-flop we are using. That is T0. And second flip-flop I am using, which is I have made it as or named it as T1. Now here we will find out the input applied to the T0 flip-flop and input applied to the T1 flip-flop. For that particular case, we will use the excitation table of the T flip-flop again. Now here in this case, just I will go through these points. We need to prepare a design table for the selected flip-flop. Then we are using the T flip-flop, so excitation table of the T flip-flop we will prepare a design table. Here the design equations for T1 and this will be the T0 are the inputs from inputs and sum are the prepared using the K-map for the above system, that is the PS1, and this will be the PS0 and XY. That's all. Now here how we have prepared or how to prepare these values, that is T0 and T1. Look at here. I have marked some color combinations. Now here if we are changing from PS1 to NS1, that is present state 1 to the next state 1, change is 0 and 0. Now look at change is 0 0, then what should be the T applied, input applied for the T flip-flop, it should be 0. Now look at what is this input applied, it will be 0. Similarly for 0 1, I am talking about only T1. For 0 1, present state is 0, next state we want 1, input applied should be the 1. Here input applied is 1. For again 0 1, input applied is 1. For 0 0, input applied is 0. For 0 0, input applied is 0. For 0 and 1, input applied is 1 again. For 0 0, input applied is 0. For 0 0, again input applied is 0. Then for 0 and 1, here look at the 0 and 1, 0 and 1, input applied is again 1. This is 0 1, input applied is 1. Then here for 1, present state is 1, next state is 0, the input applied should be 1. Present state is 1, next state is 0, the input applied is again 1, and so on. We have prepared for this. Similarly, present state 0 and next state 0. We are present state is 0, next state we want to be 0, that is PS0 and NS0. Then T0 should be 0. Here present state is 0, next state we want to be 0. In that particular case, input applied should be 0. Similarly, I will take the random cases. Now here present state is a 1 and next state we want 0. Present state is a 1, next state we want 1. In that particular case, input applied should be the 1 for this case, that is for T0. And so on. I will take another random case here. This is 1. PS0 is 1 and NS0 is 0. 1 0. 1 0, input applied should be the 1. Here input applied is 1, and these outputs are same as I discussed previously, and so on. Means indirectly we are able to prepare this design table by using the excitation table of the particular flip-flop. Here I have selected the T flip-flop. In that particular case I am using the excitation table of the T flip-flop. Otherwise I will discuss about the selection of the other flip-flops maybe in the coming video. Now here, after preparation of the design table, look at here, after the preparation of the design table, we have to prepare the equations. Now here, we have the PS1, PS0, X and Y. These are the 4 input combinations available to us. And we want to prepare the equation for input to the T flip-flop 1, input to the T flip-flop 0, and equation for the sum, that is nothing but the output, which is the sum in this particular case. Now here, if we are entering these values, here into the K-map, this is 4 variable K-map. I have taken this is PS1 and PS0 on this side, this is PS1, this is PS0, and this will be the X and this will be the Y, and I have taken this, and after preparation of the equation, this is the equation, that is Boolean expression. Similarly, we have to prepare the Boolean expression for T0, and here for T0 input, and this is for T1 input, we have prepared the Boolean expression. This is the Boolean expression, and finally we have prepared the Boolean expression for, finally we have prepared Boolean expression for sum. This is 0, this is 1, that's why here sum is equal to PS1. And by using these equations or Boolean expressions, we have prepared the circuit diagram. This is Boolean expression for the T0, this is for T1, and this is for the sum, that is nothing but final output. This is sum, that is final output. This is X, this is Y, this is PS0, and this is PS1. I have taken here its complements or bar. We can take the bar from this side also. From this, that is a PS0 complement, and here will be the PS1 complement, and so on. Now look at here, this is our output. This is our output. This output purely depends on only PS1, that is present state of the machine. That's why it is the Murray circuit. Because if we are recalling the definition of the Murray circuit, in that particular case, output purely depends on the present state of the machine. Sometimes maybe PS0 and maybe PS1, or only sometimes maybe PS0 and maybe only on the PSN, or combination of both. Because the format will be something like this. This is always for any digital system design. If this is the state, and if we are going for the synchronous sequential circuit design or any sequential circuit design, always this format is something like this. These are the states. This is combination circuit, input combination circuit, output combination circuit. Here may be the input, this is combination circuit, and here may be the state. Again, this is combination circuit, and here will be the output. This is optional sometimes. Sometimes this is also optional, and in some cases both are needed. Look at here. This is the input combinational part. Input combinational part. These are the states of the machine, and here is the output combination part. Here output combinational part is absent because directly we have the equation, that is sum is equal to PS1. Means here in this particular case output combination part is not existing for this particular design. Means these are the things for the implementation of the synchronous sequential circuit by using the Mealy model as well as Murray model. In the next video, I will discuss about the sequence detector using Mealy model and sequence detector using Murray model. I am taking these examples for Mealy as well as Murray parallelly, because the one should understand the conceptual difference between the Mealy design and Murray design. Thank you for watching this particular video. That's all.